Imagine a tall chimney standing perfectly still in the wind. The wind is steady, the structure isn't moving. Nothing seems unusual, but after some time, something strange can happen. The structure begins to vibrate, not necessarily in the direction of the wind, but from side to side. And under the wrong conditions, those vibrations can become surprisingly powerful. So, how can a seemingly steady flow create an oscillating force? The answer lies in something happening invisibly behind the structure. When fluid approaches a cylindrical object, it has to move around it. Near the front, the flow slows down and pressure rises. The fluid then accelerates around the curved surface. But as it moves towards the rear, it encounters an adverse pressure gradient. The boundary layer loses momentum and can no longer remain attached to the surface. The flow separates. And behind the cylinder, a wake begins to form. But this wake does not always remain perfectly symmetric. At sufficiently low Reynolds number, the flow can remain relatively steady and symmetric, but as inertial effects become stronger, the wake becomes unstable. A small disturbance grows. A vortex forms and sheds from one side, then another forms on the opposite side, then another and another. The wake has developed a repeating pattern. This alternating pattern is known as von Kármán vortex street. Vortices are shed periodically from opposite sides of the cylinder and transported downstream. What appears to be a simple flow around the simple shape has now created an organized unsteady structure in the wake. And this is where things become interesting. Because every time a vortex forms and leaves the cylinder, the pressure distribution around the cylinder changes. When a vortex develops strongly on one side, the pressure around the cylinder becomes asymmetric. This creates a lateral force. When the next vortex forms on the opposite side, the direction of that force changes. So the cylinder experiences an alternating force. Left, right. This periodic aerodynamic or hydrodynamic loading can force the structure itself to vibrate. This phenomenon is known as vortex-induced vibration or VIV. But vortices don't shed randomly. Under many flow conditions, they shed at a characteristic frequency. Engineers describe this behavior using a dimensionless quantity called Strahol number. It connects the vortex shedding frequency with the flow velocity and a characteristic dimension of the object. This means that if we know the geometry and flow conditions, we can estimate the frequency at which the fluid will try to excite the structure, and that frequency becomes extremely important. Every structure also has its own natural frequencies. Push it, disturb it, or excite it, and it naturally prefers to oscillate at certain frequencies. Normally, vortex shedding may create relatively small vibrations. But what happens if the frequency of the fluid forcing approaches one of the structure's natural frequencies? Now the interaction can become much stronger. The fluid is effectively exciting the structure near a frequency at which it naturally wants to move. In vortex-induced vibration, something even more fascinating can occur. As the structure begins to oscillate, its motion changes the surrounding flow. The changed flow then influences how the vortices are shed. The vortex shedding influences the structure again. So now we have a feedback loop. Flow affects structure, structure affects flow. Under certain conditions, the vortex shedding frequency can synchronize with the structural oscillation. This region is called lock-in, and vibration amplitudes can increase significantly. This entire interaction is difficult to understand by looking at the structures alone. This is where computational fluid dynamics becomes powerful. CFD allows us to look inside the flow. Velocity contours reveal the way. Pressure fields show the alternating loading on the surface. Vorticity reveals the formation and transport of individual vortices. And time-dependent simulations allow us to measure the shedding frequency itself. Suddenly, the invisible mechanism driving the vibration becomes visible. But if the structure itself moves significantly, the problem becomes more complex. Now the flow changes the structure, and the moving structure changes the flow. Engineers may need to couple fluid dynamics with structural mechanics. This is called fluid structure interaction or FSI. Instead of asking only what forces does the fluid generate, we now ask how does the structure respond and how does that response change the fluid. This isn't just an interesting laboratory phenomenon. The same fundamental physics appears throughout engineering. Tall chimneys and towers interact with atmospheric winds. Offshore risers and pipelines experience ocean currents. Heat exchanger tubes are surrounded by flowing fluids. Cables and slender structures experience aerodynamic loading. Even large civil structures can experience complex interactions between flow and structural motion. Different scales, different fluids, different structures. But many of the underlying physical mechanisms are closely related. So what can engineers do? One approach is to change the flow itself. Helical streaks can disrupt coherent vortex formation. Fairings can make the body more streamlined. Geometry modifications can alter separation and wake behavior. Engineers can also modify structural stiffness, damping, or natural frequencies. The goal is not always simply to make the structure stronger. Sometimes the smarter solution is to change the interaction between the structure and the fluid. So let's connect the entire story. Flow approaches a bluff body, the boundary layer separates, the wake becomes unstable, alternating vortices are shed. These vortices create fluctuating pressure forces. The forces excite the structure begins to move. And if that motion becomes strongly coupled with the flow, the interaction can amplify. A phenomenon that begins with something as simple as flow past a cylinder becomes a complex fluid structure interaction problem. And this is one of the most fascinating things about fluid mechanics. The flow around us is filled with structures that we cannot normally see: vortices, boundary layers, pressure fluctuations, instabilities. CFD gives engineers a window to this invisible world, but understanding the physics behind these contours is what turns simulation into engineering insight. At PRISM CFD.AI, that's exactly what we are going to explore. See the physics, understand the flow, engineer it better. If you want to go deeper into fluid mechanics, CFD, turbulence modeling, and computational engineering, explore the PRISM learning resources and upcoming structured courses. And subscribe to PRISM CFD.AI because in the next episodes, we will use the same approach to investigate more fascinating questions. Why does the flow separate? Why does turbulence suddenly appear? And how can a tiny change in geometry completely transform a flow? I will see you in the next one.